recording here. Okay, so we're in section 2.3. Hey, this is the theorem I wanted to show you, Theorem 8. This is called the invertible matrix theorem. Okay. It says let A be a square matrix. Well, you know, Binyam, welcome to 200 level math. The following statements are equivalent. That means they're either all true or all false. So for instance, if you have an invertible matrix, like statement A says, if you have an invertible matrix, then statement C says that you have to have n pivot positions in your matrix. So if you have a column that does not have a pivot position, okay, that means the matrix would not be invertible. Okay. If the matrix A is invertible by part A, then part E says the columns of A form a linearly independent set. H says the columns of A span Rn. Well, if the columns of A span the Rn space, then A is an invertible matrix. One implies the other. So this is a very nice theorem. And you're right, Binyam, a lot of them build off of each other. A lot of them build off of each other. Giving you a moment to look. I'm giving you a moment to look at the theorem. How many of you would like to prove a few of these results? How many think it might be nice to prove a few of these? Would it make you feel comfortable, a little more comfortable, if we proved a few? Okay. It would be, Wastina. So, Moshe, we can't avoid it. You know, we have to try to prove a few of these. And, you know, your next exam, hey, you could be asked to prove a few things. So let's go ahead here and look at an example. So yeah, I'm not expecting you to copy all this down right now, okay? You're not doing that, right, Solomon? Oh, Moshe was? Yeah, you really, it's in your book, guys. It's in your book. Just snap a photo of it, okay? Just snap a photo, because I want to try to get to this example. It's going to take you a while to copy all that down. Christy says she's going to drop it in the group me. I don't know what that is, but I'll let Christy take care of that. All right, so let me bring up a file here. So you have your ebook, right? You have your ebook. You know, so you can have that, you know, open, like, you know, you have the Blackboard, the class session open, but you could have your ebook open also. All right, so this is Math 284. I put 283 by accident. It's 284. Okay. Okay, so we're going to show that if we have a square matrix, and we're assuming A is a square matrix. For invertibility, you have to have a square matrix. Show that if A is invertible, if A is invertible, then the columns of A span Rn. Okay, so this is like taking a statement P and showing statement P implies statement Q. Okay, how many maybe have seen that kind of notation in another class? One statement implies another statement. Okay, Solman's seen it. Discrete math. Thank you, Christy. All right, let me give you a moment to copy this down. Okay, so we have a matrix, and we want to show that if A is invertible, then the columns of A span R sub n. So like for instance, if we had a 3 by 3 matrix, matrix A, 3 by 3, and it were invertible, then the columns of the matrix A would have to span R3. And what we're doing here in the invertible matrix theorem is we're taking statement A. Really what this is here is we're taking from the IMT. What's that stand for? It's not EMT, it's IMT. IMT stands for what, do you imagine? I'm going to use that abbreviation. IMT stands for the invertible matrix theorem. Good. In the invertible matrix theorem, and you know, everybody does need the ebook. Everybody needs to have, you know, either a physical copy of the textbook or the ebook for this course, right? But in section 2.3, what I'm doing is I'm showing that statement A implies statement H. That's what I want to do. Okay, so statement A implies statement H. P implies Q. I just wrote that in general. That's not, I mean, that's fine, but this is really what we're doing here. Okay, so let's go ahead and get to the proof here. So we have to start off with that A's invertible. Okay, we have to start off with A's invertible and then arrive and then prove the result. So, okay, what does it mean if A is invertible? Well, certainly if A is invertible, then X will equal A inverse times B. Let me give you a moment to copy this. I've written the matrix A out in terms of its column vectors, A1, A2 up to AN. Every column vector is n by 1, and those are the, these are the columns of A. Okay, take a moment to copy that. And this one part, the reason this is true, I actually showed this before, so I'm not going to include this in my solution because I actually showed that on the whiteboard. We know that if A is invertible, X will equal A inverse times B. That we know. And I showed you why earlier. Okay, so if our square matrix A is invertible, then for every vector B in Rn space, Ax equals B has the solution X equals A inverse times B. Now somehow we have to relate this. We have to relate this to the span of the column vectors of the matrix A. I'll show you how we do that. Are we ready to go to the next page? And please stay in the session now. I want to make, see, I'll just say I'm a little worried. I see a few people have left the session. I hope they come back. But all right, so good. Kevin's back with us. Good. All right, Solman's still, all right, copying it down. No problem. So the key here is that if A is invertible, then the system of equations, Ax equals B, has the solution set X equals A inverse times B. How can we rewrite? Can we rewrite? Okay, great, Solman, thank you. Can we rewrite this matrix equation, Ax equals B, another way? This is a matrix equation. But the matrix equation is equivalent to what other kind of equation? Is there another representation? Well, it is a linear system of equations, but we can also write this matrix equation as a vector equation. That's right, Robin. That's right, Westina. And that's what we're going to do. So, equivalently, since AX equals B has a solution for every vector B in Rn space, then equivalently, the vector equation, this just means it's another way of writing A times X equals B. This is just the corresponding vector equation. How many recall that? From chapter 1. Sure. And in this case, it's going to be very helpful because now we're saying that this vector equation, x1 times a1 plus x2 times a2 plus dot 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 plus xn times an equals b, it has a solution for every vector b in Rn. And remember what those A1, A2, AN, what were those? What did they represent? The vectors of A. That's right, the column vectors of A. So therefore, the span of the columns of A has to equal R sub n. Absolutely beautiful. So what, and you know, so what is, I mean, practically speaking, if the span of the columns of A, if the span of the columns of A, okay, Binyam, I'll get I'll during when our class ends, I'll show the entire thing again for you. But if the span of the columns of the matrix A equals Rn, that means that any vector in Rn space can be written as a linear combination of the column vectors of A. I mean, that's what this is, right? That's what we have here on the left. This is a linear, trying to write it as good as I can write it here. This is a linear combination of the column vectors of A. Okay. I mean, actually, that may not be that isn't actually, that is actually not, I mean, it's good, but basically, if the span of the column vectors of A equals R sub n, that means then that any vector B in Rn space can be written as a linear combination, that's what we have on the left here, of the column vectors of A. Every vector B in Rn space is a linear combination of the column vectors of A. Hence, the span of the column vectors of A equals Rn. How many think that's absolutely cool? Yeah, yeah. In other words, you could think of it like this. You could think of it like this, too. Is the vector B is B in the span these are A's here. Is B in the span of A1, A2 up to AN? Based on this vector equation here, and the fact that there's always a set of weights, x1 to x2 up to xn, such that the linear combination of the column vectors of A equals the vector B. Can we say B is in the span of these vectors, these column vectors of A? Yes. And in fact, any vector B in Rn will be in the span of the column vectors of A, of the matrix A. Hence, the span of these columns of A will be equal to the Rn space. Okay, so we can say the columns of A, I guess I should put in this final statement here. Let me see here. To be honest, it is true what I'm saying. It is true what I'm saying, but I mean, this is sort of this statement here is nice, but it's not exactly what we wanted to end up with. What we wanted to say is, you know, 3 dots. Hold on. Watch this. Maybe I can do this. I learned something new, but I guess oh, that won't work too well. That's not big enough. Three dots here. 3 dots means therefore. Therefore, I'll just write therefore. I'll just write it. therefore, the columns of A, of the matrix A, span Rn. So what I'm saying is, in the proof, I'm not saying this is wrong, but we don't need this. We don't need this here. It's true, but we could go right from here to here because of the vector equation. The vector B is in Rn. The vector B is in Rn space, and we're guaranteed that for any vector B in Rn space, there will be a linear combination of the column vectors of the matrix A that equals B. Therefore, the columns of A, the column vectors of A, span Rn. So we can go right from here to here. We don't need this statement here that I was talking about a little bit. It's nice, but it's not really necessary in the proof, you know. Does that make sense? Let me see. Binyam says, I like how this builds on, yes, span, linear combination, and adds the concept of an inverse. Absolutely. You are going to be making a lot of connections in section 2.3. A lot of connections, for sure. And I don't have any homework posted for 2.3 yet, because I know you're focused on your getting your exam and your remedial problems done. Remember, the exam, even though you can always look at your exam, your results in MyMathLab, if you need to see again which questions you missed, take note of those questions you missed and then work on them in the first remediation, second remediation, and third remediation of the exam. So now for Thursday, there are some assignments posted. I think there are 3 homework assignments because, you know, I don't want everything to be due on one day. However, if you're pressed for time, use the extensions on the homework assignments and focus on getting the remediations done. So because, you know, you have to turn in your work by midnight, your solutions by midnight on a Thursday. Okay, and I want everybody in class on Thursday. Okay, I always worry about having things, you know, due after class. I'm worried students are going to skip class. Please don't do that. Okay, I hope you know you won't do that. Okay, but are there any questions on this?